Question number 2 has a rigid 100-liter vessel. Initially contains a mixture of liquid water and vapor at 160 degrees Celsius with a 60.5% quality. The mixture is then cooled until its temperature is 110 degrees Celsius. The first thing I want you to do is draw a completely labeled TV diagram for this process. That's with 4 points. Okay, so let's do this. Let's write some things down. State 1 is a temperature 1 that said it's equal to 160 degrees Celsius, and a quality of 1 is equal to 0.605. I'm putting it in decimal form. Okay, State 2. State 2, all I know is temperature 2 is equal to 110 degrees Celsius. That's all I know here. Okay, so let's draw our TV diagram. TV diagram. This is a liquid water, so we're going to be having this vapor dome. And we know that we're at saturation at state 1. Okay, so we're going to be dealing with something here that's going to be 160 degrees Celsius. And I'm going to draw a pressure line through this. We could find out what that pressure line is. But we're going to be somewhere over here. Maybe this is going to be our state 1. And we're going to go to state 2. And that state 2 is going to be on another pressure line. And I'm going to draw this to be 110 degrees Celsius. And I have to figure out where state 2 is. Now, the key thing that I need to tell you that in this problem is I'm saying that it is a rigid tank. So if it's rigid, that means the volume remains the same. And it's a closed system, so the mass remains the same. If the volume and the mass remains the same, that means that the specific volume must remain the same, because specific volume is volume over mass. So volume 2 is the same as volume 1. Mass 2 is the same as mass 1. So you know that you must be somewhere on this line when you're drawing your state 2. And so it's easy to say that state 2 is going to be right below state 1, and the process line is going to go like this. You're going to go fall directly down here to state 2, and that is where your TV diagram is going to show up. Not the scale. I'm not perfect on this. It's just showing me a representation of how things are going to go. Okay, so now it says calculate the heat transfer required for this process in kilojoules. Okay, heat transfer means I'm going to have to deal with the first loss, so delta KE plus delta PE plus delta U is equal to Q minus W. I know that the kinetic energy and potential energy effects are negligible here. I also know that it's a rigid tank. So again, I'm going to have no work that's going to happen here. And so I end up with that mass times U2 minus U1 is equal to my heat transfer Q. Okay, now I need to do some things to help myself set the state here. And I need to find out a couple things. I don't know what the mass is, and I don't know what the internal energies are. So for the mass, I'm going to have to take into consideration that mass is equal to volume all over specific volume. And I've given the volume, it's a 100-liter tank. So we have to say that volume 1, 100 liters, and we do our conversion that we did in the previous problem, 10 to the minus third meters cubed over 1 liter. So we're going to get 0.1 meters cubed is going to be my volume of my tank. Okay? So I need to find out what specific volume is of 1 and what my internal energy is at 1. So for the specific volume of 1, I'm going to use my quality equation, VF plus X times VG minus VF. And I'm going to go to 160 degrees Celsius and find out what those values are. And if I do so, 0.020 times 10 to the minus third, remember that, plus my quality, 0.605 times VD, which is 0.3071 minus 1.1020 times 10 to the minus third. Okay, plug, and now we can chug along that my volume, my specific volume at 1 is going to be equal to 0.1862 meters cubed per kilogram. And that can help me find my mass. My mass is now going to be 0.1 divided by 0.1862. This is going to be meters cubed. This is going to be meters cubed per kilogram. Our units will set us free, help us make sure that we're doing things correctly. And we'll find that we're going to have a value of 0.5371 kilograms. Okay, that is going to be an intermediate number that we're going to use in our calculation. Okay, so now I found out what the mass is up here. I now know what this is. U2, I can find that using U1, I can find that using the quality equation again. So I know that U1 is going to be equal to UF plus X times UG minus UF. And so that, if I look this up, I'm going to find 674.86 plus 0.605 times 2568.4 minus 674.86. And I can find that my internal energy at 1 is going to equal 1820.45 kilojoules per kilogram. And that makes sense, about halfway, a little bit more than halfway along that line. And so that gives me U1, and this is going to be another intermediate calculation. The only thing I'm missing is U2. And what some students think is, okay, because I went straight down from 1 to 2, that means the quality at state 1 is the same as the quality at state 2. And that is not the case. Because as you out there at the little bottom, and even though we're going straight down right below it, we may be, that line's a little bit longer, we may not be 60.5% along that line. We're going to have to find out what the quality is at state 2 first, and then use that to find out what our internal energy is at state 2. So how do we do that? Well, I do know that the specific volume of 1 is equal. That specific volume at 2 is equal to VF plus X times VG minus VF. And in this equation, I know everything but X. And so I will solve for X. So here's what we have. V2 is going to be equal to 0.1862 meters cubed per kilogram. Is going to be equal to 1.0516 times 10 to the minus third plus my unknown X times 1.2116 times 10 to the minus third. And this gives me an X value. X is equal to 0.1531. And you're going to look at that and say, there is no way, Wanklyn, there is no way that my quality X is equal to 0.1531. Because look at my picture, it looks like it's more like, and here's where this little diagram you drew is incorrect. You did not draw it to scale. It just didn't work out that way. In fact, your scale, it probably looks a little bit like this. Your water diagram looks like this and goes way over like this when you're doing it. And so if I were to draw my constant pressure lines, and now I'm at 60, and I'm down here, maybe that doesn't show you exactly that it's 1.1, 15% of the way along that line. But I want you to understand, this is not the end-all be-all, that diagram you drew. We're not going asking you to draw perfect diagrams, but your water diagram is going to look more like the picture that I have here in the blue lines than it is with the one with the red line on it. So it is okay. It is correct. It may make you feel a little uneasy, but it is correct. Now we can find out what our U2 is. So U2 is going to be equal to UF plus X times UG minus UF. And that's going to give me 461.14 plus 0.1531 times 2518.1 minus 461.14. And that's going to give me a U2 value of 776.06 kilojoules per kilogram. So now we have everything we need to know to solve our equation, and so we can say that Q, heat transfer, is equal to 0.5371 kilograms 0.06 minus 1820.45. And this is going to give me kilojoules per kilogram. My kilograms are going to cancel, and I'm going to have in here minus 560.94 kilojoules, and that makes sense to me. As I'm going down, as my heat is being removed from the frigid tank, I should have, or as my temperature is being taken down, my heat should be removed from that situation to get this final answer. So I'm okay with that number. Looks reasonable to me, and I've gone through a lot of again rigmarole to try to understand how do I get to this result, understanding how to use the first law and how that works with quality in this equation.